Well, hello, Will, again, and welcome to our journey into number theory, where we're looking at the prime number theorem, and we introduced these two functions, psi and theta, and we finished up with this connection here, this theorem 6.2, which connects theta with our pi of x function with these two integrals. And we're going to need these, in fact, in a moment to prove the following, which is where we finished last time. This is our main theorem here that tells us that pi of x log x on x goes to 1, so that this limit exists and goes to 1 if and only if theta of x on x goes to 1. That is, this limit exists and goes to 1, and we've seen before that's equivalent to saying psi of x on x goes to 1. So that's what we're going to do now, is to prove the equivalence of these three. Now we've already seen that these two are equivalent, so I'm going to assume I'm going to assume that pi x log x on x goes to 1. That is the prime number theorem. We're going to show that that implies this result, and we're going to use part A of theorem 6.2 to do that. And then we're going to assume this one and show that implies this one, and that will use part B. And I probably won't go through that. I'll leave you to check the proof the other way. So here is the argument here for this. We've already, as I said, we've already proven that B and C are equivalent, so I'm going to assume that A holds. That is, that pi of x times log x on x, that limit exists and goes to 1. And using part A of theorem 6.2, connecting these via this integral, we can prove the result we're looking for by simply showing that this integral here goes to 0 as x goes to infinity, and then assuming that this one exists and goes to 1 as x goes to infinity will imply that this also goes to 1 as x goes to infinity. So we analyse this integral here and show that it goes to 0. So by our assumption, we're assuming that pi t log t on t goes to 1, and that means that's the same as saying pi t on t is big O 1 on log t, if t is bigger or equal to 2. So, looking at this integral, I can replace the pi t on t as big O 1 on log t, and so we consider then this little integral in here, the so-called logarithmic integral. And one way of dealing with this is to split the interval from 2 to x up to 2 to root x and root x to x. This is often a little trick you can do. Enables you to analyse each bit of this separately in the hope that it gets you somewhere. So I split the integral up into 2 bits. I'm going to guesstimate the size of this. The length of the interval is roughly root x. Well, it's root x minus 2, but that's less than root x. And the maximum of the integrand is going to be at log 2. Same here, x minus root x is the length of the interval we're integrating over, and it has its maximum at 1 on log root x. And you can see that this term here goes to 0 as x goes to infinity. And that means this integral is going to 0 as x goes to infinity. That proves that A implies B, and then I will leave you to do the other way around. You do a similar argument, except this time you have to show that this integral goes to 0 using part B of theorem 6.2, and I'll leave that as a little exercise there. So we've got now a number of equivalent forms of the prime number theorem. There are many others, and I'm going to use equivalence C, that is, that psi of x on x goes to 1, to prove the prime number theorem. So you recall, perhaps if not, you can go and look it up, that the corollary to theorem 3.8 we did quite a while ago was that the minus the logarithmic derivative of zeta was the Dirichlet series of this von Mangold function. And what we're going to do now is to prove that this minus the logarithmic derivative of zeta is given by this integral involving psi. And the reason we're going to do that is we're going to then invoke the Vena Ikihara theorem, which we can then apply to this to show that to show in fact this result up here. So firstly, just to go through the proof of this one to get this nice connecting integral. So here's the proof of theorem 6.4. So that's the statement of the theorem. And again, we just recall what some of these things mean. So psi of x, remember, is the partial sums of the von Mangold function with psi of naught as naught. And I'm going to apply Abel's identity again. This time for my an is the von Mangold function. So the partial sums of this are going to be my psi of x. And I'm going to take my f of x in Abel's identity to be 1 over x to the s, keeping in mind that we're going to be trying to get to an x to the s plus 1 up here, so I'm going to be differentiating this when I apply Abel's identity. So applying Abel's identity, we simply end up with an fn, which is this. We take that infinite sum, and that's the limit of psi of x on x to the s in Abel's identity. And then we get minus a certain integral. We have to differentiate this one. That's going to give me minus s over x to the s plus 1. And we're multiplying that by the a, and then the two minuses cancel, and I end up with this expression here. Now, what we need to do to get the result we're looking for, if you compare that with what we've got at the moment, we know that the left-hand side is the same as this minus logarithmic derivative of zeta, and we've got the integrals matching. I just need to get rid of that limit. So we need to analyse the limit here and show that this is 0 as n goes to infinity. Remember, s is bigger than 1. So we recall again that we can replace the left-hand side with our logarithmic derivative of zeta, which we want. And by the way, the fact that s is bigger than 1, and it's an exercise to show that psi of x is less than 2x, you can use that to show that both this limit and this integral both exist, that the improper integral converges and the limit exists. Now, to attack the limit, we just remind ourselves that this psi of x could be written in terms of our theta function, and we can simply get a bound. We've seen a bound on this before. This is just log 2 of x times x log x, and we change from log 2 to log e. We get this expression. So psi of x then is less over x to the s. We divide both sides by x to the s. We get this, and you can see if s is bigger than 1, then this will be a negative index up here, and that's going to go to 0 as x goes to infinity. And that leaves us with what we wanted. So the left-hand side was this Dirichlet series for the von Mangold function, which was the minus the logarithmic derivative of zeta, and it equals the integral on the other side. Now, we can now analytically continue this, so we extend the above formula by analytic continuation to the complex plane for the real part of s bigger than 1. And I make a change of variable in the integral. I'm going to put x as e to the u in the integral, and you'll easily check this pops out. And this is all valid for sigma bigger than 1, where s is sigma plus it. Now, by theorem 5.4, we've seen that zeta of 1 plus it is not 0 for all t. And we've also seen that zeta and zeta dashed are bounded for sigma bigger or equal to 1. And that means that this expression on the left represents an analytic function which is analytic for sigma bigger or equal to 1, except at s equals 1 we have a simple pole with residue 1. So I'm now going to state without proof this rather interesting Vena Ikihara theorem, which if you look at the details, as we'll see, it looks like it was just made for this particular situation. And it says if a of x is a non-negative, non-decreasing function of x, and a of 1 is less than 1, and suppose further that this improper integral, a of x e to the minus sx, converges for sigma bigger than 1 to some function f of s, which is analytic, except for some simple pole at s equals 1 with residue 1, then it says that this limit e to the minus x times this a of x is 1. Now the proof of this is long and technical, which will not be given here. You can find it in books on the subject. And now we can simply invoke that to prove the main result that we wanted, and that was psi of x on x goes to 1 as x goes to infinity. So we apply theorem 6.5, the Vena Ikihara theorem, to this integral that we had above, where this time we're taking a of u to be psi of e to the u. F of s is my zeta minus zeta dashed on zeta. And these, of course, by what we said above, these satisfy all the required conditions, and we can therefore conclude that psi of e to the u on e to the u goes to 1 as u goes to infinity, and that simply replacing this e to the u with x gives me the result that we wanted. And this one we've shown, so that shows this limit exists and equals 1, assuming, of course, the Vena Ikihara theorem, and that gets us back to the prime number theorem, because that's equivalent to it. So the prime number theorem now follows from theorem 6.3. I just put a little note here on the error term. So roughly speaking, we've proven that psi of x is x plus little o of x. And if I write this as x plus some remainder, what can we say about this remainder? Well, de la Valliere-Poisson showed that this remainder is big O x e to the minus alpha root log x for some positive constant alpha. The best known to me estimate is r of x is x e to this expression, and that goes back to 1958 to Vinogradov and Korobov. On the other hand, if the Riemann hypothesis is true, it can be shown that when you integrate psi and you get this function psi 1, then this is equal to, this integral of psi is a half x squared plus big O x to the 3 halves. Despite this, the exact order of psi of x is unknown, even assuming the Riemann hypothesis. So it still remains a complicated, interesting object. Now I spent a little bit of time looking at the so-called Mertens theorems, and we proved back in the very first chapter that sigma 1 over, or in fact the second chapter I should say, I think, is that sigma 1 over p diverges. So I should actually, I think this was our second chapter we did this, I can't remember now. Second chapter, that if you take the reciprocals of the primes, that diverges, but we'd like to know what the true order of this partial sum is. If I stop the sum where p less or equal to x, we'd like to find the true order of this thing. And we have a number of theorems traditionally called Mertens theorems, proven by Mertens, which will answer this question for us. So I'm going to assume two results, which are not very hard to prove. Firstly, if we take u of n to be the unit function, and x is bigger than 1, then the partial sums of the convolution of f and the unit function can be shown to equal the sum j less or equal to x f of j times the floor of x over j. It's a little exercise. And also that psi of x is less than 2x. That's another little exercise to show. Now, the first of these Mertens theorems says that if we look at the partial sums of log n on n, then this partial sums are log x and plus big O1. And go through the proof of this one. So the proof's just little calculations here. So if x is bigger, so that's what we're aiming to prove. We want to prove the partial sums of this are log x plus big O1. So I'm going to put capital S of x to be the partial sums of log of n, and I'm going to write L of n for log n. And again, it's easy to show that if you take the convolution of the von Mangold function with the unit function, you just get log n. That's an easy exercise. So this Sx, which was the partial sums of the logs, I can just replace with this convolution. And one of the results I just mentioned that I've assumed is that this convolution, this sum of the convolution is equal to this sum, using result 1. And the usual trick, we're going to write the floor as the integer minus its fractional part. So I can split this up into 2 bits. And I want to show this bit here is not very big. So this sum with the fractional part, these are all less than 1, so this is less or equal to the partial sums of the von Mangold function, i.e. psi of x. And the second result I assumed it was that psi of x was less than 2x. And 2x, of course, is big Ox. So we'll just hold that idea there. Now, the Sx, by definition, was this partial sums of the logarithms. And I can just use our standard sum to integral formula that we've used back in earlier chapters. So this is just equal to the integral from 1 to x of log t plus big O log x. I can integrate this as x log x minus x plus big O log x. And now that tells me then I can reorganize what I just had before, that is this sum of x. We had back here x log x, x times the partial sums of von Mangold on n. That's going to be my Sx plus this thing, which is big Ox. So that's all I'm doing here, using that result here. This one then is big Ox, and my Sx was x log x minus x from up here, plus big O log x. And finally, dividing everything through by x gets me that this is log x, plus this is going to be 1, this is going to be big O1, this is big O log x on x, and so you can hide all those in a big O1. And that's the result we had to prove there. The next result is Theorem 6.8, and Theorem 6.8 is telling me that log, here it is here, this is Theorem 6.8. Theorem 6.8, this is the second of the Mertens theorems. That if x is bigger than 1, p is prime, then the partial sums log p on p is equal to log x plus big O1. And again, I'll go through the proof of that. Again, it's just fiddly little proof. So here it is. Now remember that the von Mangold function of n was just log of n if n is a prime power. So if I look at the sum, partial sums of n less or equal to x of von Mangold n on n, minus the partial sums of log p on p, p less or equal to x, then that's going to take out the first term, and I'm just going to get this sum. It's going to be a sum over the primes less than or equal to x of log p on p squared plus log p on p cubed plus. Now this is a finite sum because eventually this will stop once we get the primes. It's simply because the prime powers are going to run out eventually from our x. So that's a finite sum, and I'm going to make it an infinite sum by just continuing it and forgetting the fact that it came from the von Mangold function. So that's now a sum of log p on 1 on p squared, 1 on p cubed. This is a geometric series now in here, this infinite sum, and I can sum the geometric series and just rearrange it, and I get this expression. We can get a bound on this by replacing p with n and take this as a sum from n equals 2 to infinity of log n on n minus 1. This series converges. It's not hard to see this by comparison. This series converges, so this is just big O1, it's some constant. And then I can then write this one then as the partial sums of von Mangold n on n plus big O1, and we've just proven that this is log x plus big O1. So that's the second of the Mertens theorems, and the main one we were aiming for is theorem 6.9, which we finally have, and that gives us the true order then of sigma 1 over p. So finally we have theorem 6.9, if x is bigger than 2, p is always prime, then the partial sums of the reciprocals of the primes, the true order is log x plus a constant plus big O1 on x. And that gives me the true order of sigma 1 over p. And the proof's a little bit fiddly as usual with these things, so we define an to be this sequence, log n on n if n is prime and 0 otherwise. That's the usual thing we do because I want to replace this from a sum over primes to a sum over n's. And so this is now the partial sums of log p on p are now the partial sums of an, and I'm going to call that capital A of x. So from theorem 6.8 above, we know that this A of x, which we did, the last result we just did, this is log x plus big O1, that's what we just proved. And this is log x plus r of x, where the remainder is big O1. So I'm going to write then the sum we're looking for, sigma partial sums of 1 over the primes. We're going to write that, well, I'm just going to write that as, I'm going to put in a log p and divide by a log p. And then the log p on p I can replace with this an. And I can replace the log p with log n because the an is 0 unless n is prime. So I can now write this sum like this. And once again I'm going to use Abel's identity. It's a very useful tool. With f of n is 1 on n, y is 1, and I'm noting that a1 is 0. So just apply Abel's identity. This is equal to this quantity plus this integral. Now this a of x we saw above was log x plus log x plus r of x. So when I do that in, I get 1 plus r, capital R of x on log x plus this integral, and the a I'm replacing with log t plus rt. So I'm using what we did above there, back up here. Now this is 1 plus, this is big O log x, and this integral I can split into 2 bits. I get 1 over t log t plus r of t on that one. So that's 1 plus big O log x. This one we can actually do the integration here. We get log x minus log 2, and we've still got this one here. So we need to deal with this integral to get rid of this. We know that r of t is big O1, and this one converges by the integral test. And so that means this is just a constant. It's just got a finite, it has a finite limit as x goes to infinity. And finally then, plugging all that back together, that means this sum is just log x plus a constant, where that constant is just what's left here. It's 1 minus log 2 plus this integral, plus big O 1 on log x. And that gives me the nice, lovely formula there for the true order of the partial sums of 1 over p. Worth noting here that the proof doesn't really give us much idea exactly what this constant is, because it involved that limit, but it can be shown that it's approximately this number, 0.026150. And I got Maple to check, a computer package to check, if I take the sum of the reciprocals of the prime, they went up to 1,000, I got 2.198. And this log 1,000 plus c turned out to be 2.194, so it was pretty good. And we'll continue on to have a look at the logarithmic integral in the next recording.